We have Jack Packet Holder from research scientist at Google DeepMind, and also honorary lecturer at UCL, working on the OpenNetNess team. We heard a lot about Genie in 2 or 3 talks. So now we have somebody representing that team, and over you go. I think that's the. What do you need?
I'm much better at generative web models than I am at laptops.
Yeah. Let's do that. It's going to happen automatically, hopefully.
Okay, that looks good. Okay, I'm just going to scrap this presenting thing and just do it. Is this one? Yeah. Okay.
Great.
I haven't done this way for so long. Okay, cool. So sad I couldn't be here. I'm sorry about the date. That was from the ICML one, but we have added new stuff since then. Sorry I couldn't be here earlier. Whoever did mention Genie, like, catch me after because I'd love to talk more about it. But yeah, here I am to talk about generative interactive environments. Thank you for the introduction and the invitation. It's super exciting. Okay, so clicking works. Okay, well, this is the team that works on the project. Super diverse interests, backgrounds. Really cool to get to work with all different people. And I think most of us in this sort of LLM era of agents now being web-based rather than more real-world, a few of us kind of got together a couple of years ago and started thinking what's missing for getting some embodied generalist agents. So an agent that, given sort of any real world scenario, whether it's driving a car, whether it's cooking food, whether it's walking my dog, it'd be really nice to do that, or even just playing a video game really well. How can we get an agent that can perform all of these different tasks in the world and also safely? And how can we evaluate it in some sensible way? And for me, the way that's we've really achieved strong agents in the past that can take actions in the world is through RL. So taking a little bit of a historical tour to the ancient era of 2013. Once we had access to things like the Atari environments, it didn't take too long for some really amazing people to work on RL and get human level performance in all of these different games. And I mean, a few years later, we're superhuman in all of them, and a few years later, you can do it in just like a few steps on your laptop. And obviously, like, we can keep doing this forever, but maybe that's not the end goal. But either way, the moral of the story is there's an agent environment duality, and really it's the abundance of cool environments that allowed this research to prosper. And then a few years later, given access to a Go simulator, we're able to get superhuman Go agents, again, given perfect access to this environment. So then going back to the kind of motivation of more general agents, this paper I think is really cool. In terms of talking about AGI, which obviously is a topic we talk about a lot, it kind of breaks it down in a quite sensible way in terms of the performance level and then the generality. So this is a paper from ICML this year. I don't have the citation here. Oh no, I do at the top. Morris et al. This is also ICML this year in the position paper track. And you see that things like AlphaGo and AlphaZero, they're like superhuman, but obviously very narrow, right? So it's it's exciting, but it's not really going to solve like a completely new task. Like, it's not going to walk my dog. It was my turn today, that's why I'm maybe a bit more annoyed about the dog. And to get to this point, it sort of seems kind of obvious, to me at least, that like we're just completely lacking any form of simulator capable of learning these like really general capabilities. And I realize and appreciate that this is very game centric, but I think you also get similar things in robotics. So, for example, you might get a really good simulator of a quadruped for a certain task, and you might get then be able to transfer it to really similar different domains, but that same thing can't then play computer games, it can't then drive a car, it's just able to do this one thing. And so really for me, the thing that was missing, and a few of the others as well, is a sufficiently general sort of environment, right? And so how can we get this? There's been a bunch of different approaches. So for example, just build it, build more capable environments. I'm not going to talk about this too much, can do in detail, but because I worked on the XLAN project at DeepMind, and also we could just stitch together everything and just train on all of it, but really that just doesn't seem like the scalable way. So instead, sort of a year before these all came out, we started noticing that video models were getting pretty good, there was a paper, I think, from like Frank Wood's group with like long diffusion video diffusion models that started looking like, you know what, like this is kind of the early signs that we got with language models that these things are really starting to work. And they really have this kind of like real world knowledge. And we thought, well, imagine if you had a video model and you could actually use it as like a simulator for the real world. Because, I mean, world models are really cool, but when you're just learning a single environment, you don't really get much value add from the world model other than sample efficiency. You don't really get, like, the really exciting thing is about creating new worlds. And the video models kind of follow this foundation model recipe where they can create new things. However, there's quite a big difference between the video models that we can maybe call a world simulator, but it's not really a world model. I mean, Jan LeCun had these points, same thing, like you can't start from the same state and take different actions and get like counterfactual experiences. It's much more high level control, and all it really needs to do is generate one cool sample, but then it kind of forgets everything about it and starts from scratch again. Whereas a world model, I think you'd want to be able to reset to the same state and then take different actions and try different things, so we can do things like RL and learn from experience. And then if we look at the kind of environments that we typically were using, at least on the more like gaming side for embodied AGI research, you see that these kind of worlds, like they have this like very low level control, but they're not very realistic. So really, like you could just take all these kind of environments and just train a world model from those, but then it's never going to have the rich real world nature from internet videos. But then if you're training the internet video model in the current paradigm of text to video models, you're not going to get a controllable world model. So the goal of our project, I added in some related work, so I'm going to talk about that first. There's a few options for how you might get around this. The first one is this Gaia 1 work from Wayve, which I think is really cool. They kind of have a kind of structural edge, right? Because they collect huge data sets from driving around London, mostly like nice rainy streets, of the cars driving around, all kind of stuff like that. And they're able to train a pretty large world model. I think they got to around like 8 to 10 billion parameters, and they get as well some nice scaling properties that you might maybe see as kind of representative of what you would hope to continue going in the future. They are able to get this kind of like nice world model for their specific setting, and it does have this kind of compositional generality and abilities to create new worlds, but only really for driving, and only because they, and probably no one else, maybe a few others in the world, have this data set. So it's not really like kind of a scalable way to AGI, but it shows you that when you have much more data, you can get this like early signs of compositional stuff. So for example, is this going to load? I'm hotspotting on my phone. No, it doesn't look like it's going to, but I'm sure some of you have seen this already. So on the left, what you would see here is in the world you can turn left, turn right, like from the same frames. And then on the right, they can change it, so they can change to make it sunny. There you go. You can change to make it sunny, so you can, like, for example, take a typical autumn day in London and say make it hot, and then the car can see that. And you can imagine that if you only ever trained it on the data that look like what it's seen before, there's a lot of situations that would be out of distribution for the agent, that you could do some kind of curriculum over that and then robustify the agents, all these kind of different things. And so even though it's just for driving, they're already getting like quite significant benefits from being able to have a generative model over this. The second example, and this is meant to be a GIF, so it's a bit worrying that it doesn't show because I have tons more to come with my own work, is Unisim from Sherry and others at my colleagues at GDM. What they did was they kind of stitched together like every kind of data set that we had and like create some notion of an action for it. So, I mean, in the simulation environments, they obviously have actions. Some of the real robot stuff, I think they have like language goals that they were able to say was like an action. And then for some of these other data sets, they use like camera angles of like left and right and said that they were actions. And then she also used text to image data, and she said that the caption was the action and the image was like the next frame, whatever. But by stitching this together and like coming up with some weighting scheme, she basically took every data set that we had that had any form of label and then trained a single model over all of it. And Unisim is really cool because it's kind of like it's kind of just a regular video model like the others, but it's able to condition on past frames and then the next action and generate the next part of the sequence. And so it's actually a bit more like a world model. It's slightly lower level of abstraction and has some notion of environment consistency. So this video does work, but basically what you can do, this is entirely generated, is you can like continue it by changing the actions at the top. I had to truncate this because it didn't fit in Google Slides, but there's actually 6 steps. If you go on her website, there's tons of other examples as well. But this is kind of cool because you, at least at a high level, like language, you can actually treat this a bit like a world model, and it kind of resembles the task. But the negative on this approach might be that, like, Sherry obviously did an amazing job to stitch all these data sets together, but like, how much further can you go with this? Because I'm pretty sure she exhausted like most of the data sets that we know. Maybe you can add in like the RTX stuff now, but like, you need to keep collecting more data sets if you really want to scale this to like the kind of size we see with language models. And so the goal of the Genie project is kind of, in parallel with these actual other works, was how can we just do a purely unsupervised approach just from videos? And the idea was like, well, this may seem like the hardest approach to get working, but if you do get it working, then in theory, all you need to do is just ask senior leadership for drastically more compute and then just keep going and scaling data and compute like we see in other places in our field. And so the approach that we took to do this is to learn latent actions. And so if you imagine how this works, I think you might have other works in robotics that use latent actions because they have actually been used there before for things like behavior cloning. But you kind of imagine it's sort of like clustering potential outcomes. So if you have a latent action model that sees enough data and give it a small bottleneck, which we'll talk about a bit more in a couple of slides, it essentially has to figure out what are like the kind of primitive actions that are consistent across the entire data set. Then you essentially have learned action labels for the data, and then you can just go back to the races and train your video model to condition on those actions to predict the next frames. And so that was the approach we decided to take. And we are fortunate to have, as co-leader of the project, Ashley, who previously worked on imitation learning with latent actions in her PhD, so was probably one of the experts on this area. So if we look at our model, at training time, we basically take in just a video with nothing else. The video goes down through 2 different channels. So the first is the tokenizer, which is just standard like VQV, except we have this temporal component to it. But that's kind of a detail. It maps these into video tokens. And then we have the latent action model, which for the purpose of this work was learned on the fly, but really it could be pre-trained and frozen if you wanted to for a similar output. But the thing that we found in this work was that the latent action model works best when it takes the raw images as inputs rather than the tokens. It almost like learns its own representation for actions that aren't the same as the ones. It doesn't work as well if you pass the tokens to the latent action model, at least for the data sets that we used. And the latent action model basically takes in fact, do I have a slide specifically on this? No. Okay, so go on to see something. The latent action model takes in the past frames plus 1 future frame, passes all of that through the encoder, and then the decoder takes the output of the encoder plus the past frames, but not the next frame, and it decodes the next frame. So essentially what you have is the past plus 1 of 8 values, because we have a VQ codebook. So you have the past plus 1 of 8 values, and then you have to predict the future. And so essentially what you want is those 8 values to give you the most useful piece of information that you could possibly have to, given the past, predict the future. And what we see is that at sufficient scale, these 8 values end up being semantically meaningful actions like move left, move right, jump. We can go into way more Q&A and discussion about the merits of that and future work in that area at the end. But for now, that's just to say this is like a fairly magical method that takes in videos and then can produce 8 actions that make sense across the entire data set. We then have our dynamics model, which in this case was mask-git. And the idea with the dynamics model is it's basically like it's a similar approach. It's kind of in between a diffusion model and like a language model, in that it predicts, it has a cross-entropy loss, and it just has a very similar approach to sampling as a language model. But it predicts the entire image in one go, and it takes 25 steps to fill in the blanks of the image, rather than doing like autoregressive, like 1 patch at a time, which would take a really long time. With 900 patches, 900 tokens per image. You have to go like 1 at a time, that's 900 samples to get 1. And then with diffusion, at this point, diffusion was much slower as well. It needed hundreds of steps to generate a sample, whereas Masket was pretty good with sort of 25. So yeah, that was the model. And then the cool thing is that the latent action model essentially gets thrown away at inference time. So we don't really care about training the latent action. The latent action model has an encoder, which we don't really care about. But the main thing about it is that the dynamics model is trained to condition on its outputs. So its outputs are just like the action vectors that come from the codebook. So all you need is the codebook, and then any person can then say, I want to take action 0. It indexes the codebook for action 0, which is frozen, and then you condition the decoder on that, and then it will just, the dynamics model decoder on that, and then it can just predict the next frame like it's an action, which then means that all you need is a prompt image and a set of actions from a user, and then you can just treat it like any other environment, or even a game, which is kind of cool. So for this work, we focused on publicly available internet videos of 2D platform games. We get a lot, very, very different feedback from this. Some people are like, oh, obviously you just use 2D platform games because you could have used the whole internet, but you're just trying to show proof of concept, and like that's a reasonable subset with some similarity across the videos, and like good start. Other people are like, so is this just a 2D platform gaming model you produce, and like how would, like, and it's just like, okay, it's clearly not. It's the 2D platform games thing is a detail. Again, like you shouldn't really think too much about that. It's just when you're starting with this for the first time and no one's done it before, it's a reasonable starting point. But we could have said, oh, we're going to take publicly available driving videos, or we could anything else. I think it's just really design choice, and we had some gamers in the team who were excited about that. But given this data set of sort of 30,000 hours of video, we originally had 300,000 hours, and we filtered it down to 30. That's very important in general when you use internet videos because they're quite noisy. We then were able to get these kind of scaling properties. So on the left is keeping everything fixed but only increasing the model size. You just see improved loss. In the middle is keeping the model size fixed. So this is again like this is the final point for this one. And then on the right is keeping the model size fixed, I think at like 2 billion. And then just changing the batch size from 128, 256, 448. We've seen improvement in both in that as well. And then basically what we did in the end was we said, well, continuing this trend, these two trends, given our compute budget, we have 11 billion parameter model with a batch size of 512, which was trained on 256 TPU v5p for 3 weeks over the holidays. That was fun. Okay, so everything we show in this work is our distribution for kind of obvious reasons. We're not showing any of the videos that we actually trained it on. So every single image is an image that's generated by a text-to-image model. So I think we use Imagen2 is what it's externally called for pretty much everything, unless it's obviously not from that. We shall see. But essentially the model has never seen this before, right? It's literally just unsupervised trained on some 2D gaming videos from the internet, and then it's given out of distribution prompts and then just played by us to make videos, because that's kind of fun. So in all these cases, it's kind of like, it's inferring what the agent is, it's then like taking the actions and then doing something meaningful with them, and then continuing on from that, autoregressively sampling. And it kind of works, which I think is quite, to be honest, quite surprising, because it wasn't trained on that much data, and the data it was trained on definitely didn't have anything that looked like this. So that's kind of the headline result, I guess. In terms of a world model, I think we said before a really key thing is to be able to generate diverse trajectories from the same starting frame and have like counterfactual experiences. So this was kind of important for us. Even though the trajectories don't all look like amazing, you can do different things from the same starting frame. The other thing that's important is that the actions are actually quite consistent across different environments. So taking the same sequence leads to the same give or take behavior, which is pretty cool if you want to train an agent from this. And we had a lot of pushback in the first few months, so it was quite satisfying to put this kind of thing in. Like you can imagine, obviously we have colleagues and internal, external folks who literally work on every single one of these areas and didn't think this was going to work. So it was I don't know, quite satisfying for us, although maybe Drake's not cool anymore. We also played with it a little bit with other things. So internally we had a thing called Genie Sketch Challenge where we got people to like do drawings and then we tried to play them. This was the winning one. It's kind of cool because the character runs along and can actually jump up the ladder. This was one of Jeff Clune's children did this drawing, football player. And this one, I'm going to name and shame, was Ashley's. She was very proud of it, and she took around maybe 10 minutes to do it, I think. And all of these kind of work too. So it picks up on the football player here, sorry, American football player here. It picks up on the ladder, and the agent kind of turns around. And then obviously this kind of red creature thing also moves. But it respects the platform too, which is kind of cool. We went even further, so this is my beloved dog that I would love to get walked autonomously. This is a character on my manager Tim Rocktershaw's desk, and then this is a piece of pizza that we had while we were playing with the model to do these images. These ones also kind of work. I mean, obviously slightly worse because this is really out of distribution, especially the dog. In Chiswick House, for anyone it's a very nice park. But yeah, it kind of works, which I think shows that, like, given that it's quite unreasonable this would work, it's quite promising in terms of the general direction, because it can only really get better from this point. Okay, so another thing that I think was kind of cool is that the model is starting to learn some kind of notion of 3D, and this was just a 2 billion parameter model, because we got this result quite early and then we didn't bother remaking it with the later one. But taking the same action sequence in these 4 different worlds, you do see like different movement in the foreground and background. And I think this is really cool, especially because so many people working on 3D nerves and all stuff like that kept saying that it would be essential for us to do the same thing, and really don't believe so. And kind of use the analogy of language models, how like part of speech tagging was like really important, and then suddenly the language model just learns it all from predicting the next token. And it seems like this model, even at this scale, does kind of learn some like world knowledge that it can apply to completely out of distribution images. Finally, a robotics image. I should probably skip this one. But this is just the RT1 dataset. So it's from that paper, which I guess is now quite old, maybe a year and a half ago. And what we did was we just stripped the actions off and treated it like video, and then trained 1 or 2 billion parameter model on it to show that the method was sufficiently general. And you get the same thing where like a latent action sequence, this one, for what it's worth, kind of does the same thing. Like you get this kind of like jig from the arm, and then this sequence here, you again like kind of get similar-ish behavior. I think this data set's actually a lot easier than the internet videos we use because nothing else is moving. So it's not super interesting to train on this data, to be honest, because like nothing else is ever going on. You can perfectly move the arm. You could actually, in the playing tool, you can play it for ages, but it didn't really generalize because the videos only look like this in kind of moody rooms, like everything looking kind of similar shades. I think it'd be a cool bit of future work potentially to really scale up the more robotics angle. And the one cool thing about this, and again I'm speaking with zero knowledge of robotics, which Ed can attest to, I've spoken to about in the past and demonstrating my lack of knowledge, is you can see things like the bag of crisps here, where like the model kind of knows roughly how it should react to being grasped, which I think is fairly hard to do in simulation, maybe. But yeah, it seems pretty cool that it can do that. And then finally, the latent actions that we learned, we did this really simple proof of concept to show that they did actually have some value for agent training. So we take the exact latent action model that we trained on internet videos, and then we take just a handful of expert trajectories without actions from this coin run environment, and we say label that with latent actions, so like as an IDM, but latent inverse dynamics model, and then behavior clone those latent actions, and then try and learn the latent real mapping from a small labeled data set. And you can see that basically, like in just a few steps, you get as good a performance as the actual videos that you trained from. So this isn't like, okay, we've got generalist agents from the model already, but it's kind of a sign that there's like something useful going on in the latent action space. So when scaled up and maybe doing online RL in the model, which would be really cool, you might be able to learn behaviors that can transfer across. And so going to the future, I looked at 10 minutes, so I can speak for another 5 or so. The main thing is, it's kind of a cliche and a bit cringe, but it really is the worst it's ever going to be. I kind of know this is true because this is results from a year ago, but like we've just shown really the first version of this, that you can train a video world model from internet videos and play it, it's consistent, and then use it for some kind of agent stuff. But it seems like there's a lot of cool research that could be done both at large and small scale, and so we think it could enable a significant leap in embodied AGI, which I think is still pretty worth doing, even though it's not currently as in vogue. We have this paper from our team that was also at ICML, which I think is kind of interesting. It shows sort of how a genie-like model might play into a broader system to get an agent that can produce novel experiences. And you can imagine an agent training in these generative worlds with some kind of curriculum, it would generate its own worlds and then solve them. And if it could do this for a long enough period of time, it might be pretty general and also create cool worlds that you could also interact with yourself. This is fairly, I guess, sort of like, oh look, Genie's interesting because the paper I wrote says so. But as an external validation, I have Jim Fan, who I think does really cool work, and also agree that it could be a nice backbone for embodied agents. We also speak a bit with the folks at 1X. So Eric Zhang and others, they re-implemented the Genie model from our paper, and they used it for some recent blog post with some kind of cool results. They also open sourced the data set that you can use, and they open sourced the code. So you could train a Genie-like model on their data, and it seems to work pretty well. And they've actually done some like initial scaling analysis with it, which is pretty cool to show that it works in their domain too. I think the humanoid stuff is really exciting. And finally, this paper came out last week and someone sent it. And it's kind of, I think, interesting because it's showing that like latent action pre-training actually before fine-tuning with real actions could be valuable. And you can see the merit of this, right? Because go back to Sherry's case at the beginning, she had labeled data for like quite a lot of data, but not enough to really go for it. So maybe you could combine these things by like doing some kind of latent action pre-training and then like fine-tune with real actions, and it might work for real-world data sets. I think they had some like pretty good results using this. Yeah, and we also in our paper have how to re-implement everything in the small-scale setting. This was trained in like a couple of days on a single like 2018 TPU. Spent quite a bit of time trying to like write this all up so it's fairly transparent. Some students in Oxford did manage to re-implement it, and it apparently works. So if anyone's interested, you can at least. It's not open source or open weight, but it's open method, I guess. So that's it.
Alright, we have time for questions. Yes.
Thank you for the talk. Jake gave a similar one in Imperial actually a few months back, so I was there for
Whose is better?
yours is more recent.
Okay.
That's what I'm going to say. To be fair, you haven't got any new stuff in it from that. I thought you'd share some more secrets.
Yeah.
I guess my question is on threefold. So the thing with Genie that makes it really powerful is also like what you're going to see it evolving in terms of its controllability, latency, and then long-term consistency. How do you see yourself and your team tackling those three sort of frontiers?
Well, the boring answer, I guess, is scale. Because, I mean, I guess, look at like GPT 1 and 2, right? They're not going to write, I mean, they can't even really write a few paragraphs. It was cool, but like it just descended to nothing pretty fast. And then look at the latest ones, and they obviously can write pretty long, coherent things and then be responsive. Even things like, some of these things like character AI, right? They can have like long interactions that maintain consistency. So I think that, I mean, that is just kind of going to pan out. I think in terms of, there's probably some other tricks you can do. Like there was some works on consistency in the Game Engine paper that came out recently, and like there were some ideas there on like how you can like noise the past frames. They mentioned in that paper that seem interesting. Maybe some other ways of using prompts, like different ways. So there's lots of kind of tricks to get longer term consistency. And what were the other things? Latency. Controllability. Yeah, so I kind of, I mean, I did give you one new thing at the end with that, with the latent action, pre-training, fine-tuning, that is potential. But we haven't.
Books only 8 actions at that point, so right? Or is that-
I didn't actually read the paper in too much detail. It just got sent it by like loads of people, so I thought it looked pretty interesting to me. You could do something else with the latent actions. Like it doesn't have to be 8. I think 8 made sense for what we did in this work, especially because we were doing 2D platform games. But there's lots of other things you could do, make it more expressive latent action space. Yeah, but we haven't got anything publicly shareable in that domain. And then for latency, I think that was your third one, right? So that area has been actively worked on like a lot. So if you look at things even just like external competitors, like look at Runway. I mean, they have a pretty good video model. It went from being like a minute to generate like 10 seconds to like 20 seconds to generate 10 seconds. Lots of tricks like distillation, these kind of things like that. And then inference compute. So there's a lot of fairly known things that should just like be in our favor. So.
Thank you.
Right, next question.
There's one over there.
Yes.
Thanks for so I was wondering, do you think it's possible to extend this, like you mentioned, from discrete action space to continuous action space, right? So instead of discrete code book, maybe if you have continuous latent space, just standard VA.
Yeah, I don't see why you couldn't do that. There's probably enough smallish scale versions that you could try that with, I think, without too much hardware. So, interesting research direction. If you get results, happy to give feedback.
All right. Any further questions? No? I have a question. You said surprisingly it worked after you trained. Why you use the word surprisingly?
I mean, I was starting to lose faith after about 6 months. Ashley and Jake weren't. I think from the fact that like it was only trained on 200 different games, and I kind of thought out of distribution it wouldn't work with that few. I thought it might work in distribution on like things similar like what it was trained on, but the ones that you're seeing it prompted with, like the dog, for example, there really is nothing like that. And like we hand labeled our own data, so I know what the data looks like. There was nothing that looks remotely like that. And for it to actually pick up on what the agent is and apply the actions in a fairly sensible way in a completely novel domain, I think it's. I mean, not most things don't really generalize that well. Like even these fancy language models.
And why did it work?
Why did it work?
Yeah.
Magic. Deep learning. I think honestly, I think the data set was probably a huge part of it. Like we spent a long time like, curating. We filtered out 95% of our videos, and I think the fact that they're like the motion is fairly clean in them makes a big difference. So maybe that's why it worked. I think that's probably the most important thing.
All right. Okay. Let's thank Jack again. Thank you all for coming. See you in the next event. Have a nice evening.
Thank you for being
Yeah, not bad.
Very good. I might go with Mona and